Hello and welcome to lecture number 11, continuing with the concurrent assertion operators. In the previous lecture, we saw consecutive repetition operator. And in this lecture, we will see non-consecutive repetition as well as non-consecutive Goto operators. So in the previous one, we said consecutive means a given signal M with a star here should remain consecutively high or low. But there are many times when we know, or we do not know for that matter, that signal M should remain or should become high non-consecutively M number of times. Let's look at the formal definition first. This means that the signal B must be true on M clocks, not necessarily consecutive. That is, there can be a delay of one or more clocks between one match of the operand and the next successive match. Successive is important here. And no match strictly in between. And let's look at some log files to solidify the concept. Now again, just like in non-range operators, M cannot be infinite, which again, if you think about it, does not quite make sense. So let's look at what this means. At pause edge of clock, A implies that starting next clock, B should be true anytime after one clock. Do not confuse this non-overlapping operator, which means pound 1. Do not think that after A, B must arrive 1 clock later, and then it should arrive anytime after that. This is very important, and this is where many people get confused. So again, A, 1 clock later, B should be true non-consecutively twice, whenever. What that means is 1 clock later, which is a non-overlapping, B can be, the first time B can be true, can be any time after 1 clock. There can be 100 clocks here. And once it is true, 1 clock later, or just 1 clock later, or any number of clocks later, B can be true. Okay, so let's look at the simulation log file. So again, this repeats that note that the first occurrence of B does not necessarily have to happen exactly 1 clock after A. Okay, so B is not true exactly 1 clock later. It's true 2 clocks later. Then again it's true after 4 clocks, non-consecutive. And then the property passes here. So here's the simulation log file. A is true. Well, in this case, B is true 1 clock later. It doesn't have to be, but it is true. And then a few clocks later, B is true again, and the property will pass. In this case, A is true. B is not true after 1 clock, but it can be true any number of clocks after A is true. And then again, it is true a few clocks later, in this case, 1 clock later. And when this happens, the property passes. Now, let me ask you this question. Will this property ever fail? Think about it. No, it will never fail. Because what we are doing is, we are waiting for one B to be true. That the very first B may not come till the end of the simulation. Property won't fail unless it's a strong property. Or let's say the first B comes. The second B may not come until the end. It may not fail. It may be incomplete. So my point is, when you write a property, be very careful. So how will such a property fail? If you write it simply what I have done here, it will not fail. So let's look at the next slide, which again, just like in consecutive repetition operator, it is pound 1 C. 1 clock C makes all the difference. This is the qualifying or end event, as I call it. So what this means is that the signal B must be true on M non-consecutive clocks, just like we saw in the previous slide, and C needs to match after any number of clocks after at least one clock after the match of B. So may read a little confusing, but let's look at the diagrams. A is true. 2 clocks later B is true, which is fine. A few clocks later another B arrives, which is what is required and is fine. Now see this. It says 1 clock later C should arrive. Well, C does not arrive 1 clock later. That's also okay. It is the same thing here. 1 clock later, non-overlapping, B should arrive. This 1 clock does not mean strictly 1 clock later B should arrive, like we see here. B can arrive any number of clocks after A, and then any number of clocks after the first B, second can arrive, and any number of clocks after the last B, because that is equal to 2, C can arrive. C does not necessarily have to arrive 1 clock later. It can, but it doesn't necessarily. So as you can see here, C needs to match any time after the last match of B, and B should not match in between the last match of B and the last match and the match of C. If B, let's say, arrives here again on this clock, this property will fail. So let's look at the simulation log. A arrives at time 5, B arrives at time 25. A clock later, the second B arrives as required by equal to 2, and then a few clocks later, C arrives. And this matches the property and the property passes. In the previous example, I asked you, will this property ever fail? In this case, property can fail. Let's look at how. A arrives, 1 clock later B arrives, it can be any number of clocks. B arrives again. But now, once B has arrived 2 times, we must see a C any number of clocks after the last occurrence of B. So what's happening here is, we are waiting for C after the second occurrence of B. It arrives here at time 175. But before it arrives, B arrives again. And like I just told you, if B arrives here, then the property will fail right there. So because the third B arrived, property fails right there. And this is why this operator with a qualifying event becomes very useful. I want to see a signal remain true or false for that matter, or m number of times, and then after that I want to see another event occur anytime after that. But once this signal has arrived m number of times, it should not arrive again m+1 number of times until my so-called end unit arrives. Let's look at, so we just saw the non-range operator. Now let's look at the range non-consecutive operator. Here's the property, and m:(n) pound 1c means the property matches over an interval of clocks, provided A is true here on the first clock tick, and C is true on the last clock tick, and there are at least 2 and at most 5 not necessarily consecutive clocks strictly in between the first and the last match of B. So there's another way to read this property. And again, m has to be greater than or equal to 0, and n can be greater than or equal to 0 or infinite. Let's look at this log. As you can see, A is true. 1 clock later B is true. Again, B can be true any number of clocks after A is true. And minimum number of times B needs to be true non-consecutively is 2. So B is true twice. C arrives anytime after 2 B's and the property passes. Again, just like in consecutive, my question is, when will you wait for 5? Here's the explanation. After A is true, B arrives. First B arrives. And in this case, consecutively, which is fine. Consecutive is a subset of non-consecutive. B arrives. Now, what the property is going to do is, after second B, just like here, it's going to look for C equal to 1. It's going to look for C equal to 1 somewhere. There is no C equal to 1. So now it's going to wait for the third B. After third B, again is going to look for C equal to 1. There is no C equal to 1. It waits for fourth B. It waits for fifth B. And after fifth B, it must receive C equal to 1. After 2, 3, 4, it may or may not receive C equal to 1. But after 5, because 5 is the limit here, it must get a C a few number of clocks or right after B, last B is detected. But again, in the previous example, let's say after the fifth B, before C arrives, if there is a sixth B, the property will fail right there. And that's what I'm showing in this particular example. A is B, B is true twice, there is no C. Look for third, there is no C. Look for fourth, there is no C. Look for 5. Now, after 5, you must get C equal to 1. But before C equal to 1 comes, B again becomes true the sixth time. Okay? And these are real simulation logs. So simulators basically have proven what the LRM says. And here the property will fail. So again, the qualifying event is important. Again, you can read this as, if A is true, B needs to be true non-consecutively twice or 5 times until C arrives. Let's look at an example, an application. If non-burst read of length 8 is asserted, that the ready act must be asserted 8 times. You're going to read 8, or a non-burst read of 8. Non-burst meaning the 8 datas are not going to come consecutively. It's a non-burst. But you do need to get a ready act, and only with the ready act the data is meaningful. So ready act must be asserted 8 times, and ready done must be asserted anytime after the last read. And that there are no more ready acts between the last ready act and read done. This is pretty much identical to what we saw in the previous slide. So here's the property. I have purposely parameterized it with a formal called length. What we are saying is, at passage of clock, non-burst read, again, the antecedent is carefully selected, because here, if non-burst read of 8 is asserted, a length 8 is asserted, which is the antecedent, everything starts with this particular condition. So if non-burst read is asserted, then starting next clock, read act must be asserted number of times. Here length, when I assert the property, I provide an actual of 8. So the read act must be asserted 8 times. Should be found high. There can be latencies, so it's non-consecutive. But after the 8th read act, I must get read done anytime after the 8th read act. Just like we saw in the previous example. If I get a 9th read act, the property will fail. Now, so this was non-consecutive operator. There is also an operator called non-consecutive Goto repetition operator. Non-consecutive operator, non-consecutive operator, and non-consecutive Goto operator. There are 3 kinds of operators here. So what does Goto mean? What we have seen in the previous example is, now let's just look at the property without the so-called qualifying event. So here the syntax is, carefully note, there is this arrow. Okay, in the non-consecutive we had and equal to sign. So here there's an arrow. It means that the signal B must be true on M clocks, not necessarily consecutive. And there can be a delay of one or more clocks between one match of the operand and the next successive match, and no match strictly in between. And M must be greater than or equal to 0 and cannot be infinite. If you read this definition carefully, it is identical to the definition of B equal to M, meaning non-consecutive operator. And you may scratch your head and say, why do you need a separate operator if it is identical to the equal to? This operator non-consecutive with the equal to sign here. Let's continue here. Here's your two non-consecutive clocks, identical to what we just saw in the previous slides. Here's your simulation log. If A is true, B can be true anytime after A is true. Second B can be true or must be true anytime after the first B, and the property will pass, and so on and so forth. If you look at this slide, and I encourage you to go back and look at the slide with the equal to sign here, meaning consecutive, non-consecutive operator without the word Goto in it, you will see that it's identical. This whole thing is identical. So as I just said, since there is no qualifying event here, there is no AND event here, after B go to operator 2, in this example there is no difference between this example and the one with B equal to 2. It's the qualifying event that differentiates between the non-consecutive and non-consecutive Goto construct. So let's put a qualifying event here. This means that the signal B must be true on two non-consecutive clocks, and C must be true exactly one clock after the last iterative match of B. Now this is the difference. When we had an equal to sign here, #1C meant that after the last iterative non-consecutive match of B, C can come anytime after the last B. Goto means C must come exactly 1 clock or 2 or whatever you have put here after the last iterative match of B. That's the difference. That's pretty much it. There is no other difference between non-consecutive and non-consecutive Goto. So here again I have shown A, B can arrive, first B can arrive anytime after A, second B can arrive anytime after first B, but C must arrive however many number of clocks you have put here. It must arrive exactly that many number of clocks after the last B. And here's the simulation log. A arrives, B arrives, second B arrives, and exactly 1 clock as required by #1 here, C arrives and it passes. Here again, A arrives, some clocks later B arrives, a few clocks later again B arrives as required by 2, a number here. But exactly 1 clock later C does not arrive. And the property fails right there. C arrives 1 clock later. That's a bug in the design. So basically that's the difference. To repeat, non-consecutive, #1C means C can arrive any number of clocks after the last B. In the Goto, C must arrive as many number of clocks specified here after the last B. So here is the example with equal to. Here is the example with Goto, and side by side you can see from 25 to 95, 25 to 95, everything is the same. But after the 1, 2, 3, 4, 5 B's, C can arrive anytime after the last B in equal to non-consecutive operator. But in the Goto, C must arrive 1 clock later, which it doesn't, and the property fails right there. So the simulation log is identical between these two. I created a test bench so that the simulation log looks identical. In this case, the property passes. In this case, the property fails. That's it. That's pretty much the difference between non-consecutive and non-consecutive Goto. Okay, I'm trying to keep the lectures short. So we have seen non-consecutive and non-consecutive Goto operator. Thanks for attending the lecture, and I'll soon see you in the next lecture.